That is the status of the Big Bang theory as we know it today. Whoops, sorry. And what I want to emphasize is that we were led to this line of reasoning beginning with one idea, that the idea of the Big Bang was a beginning. The Big Bang was a beginning, meant it had to be a sudden event. If it was a sudden event, I had to have this inflation. Then if I have to explain the later data, I needed the dark energy. That was the line of argument, okay? There's no way out of this line of argument, as long as you consider the Big Bang as the beginning. So if you want to get out of it, if you're not satisfied with it, I think there's only one way to go, and that is to go back and rethink that idea. We don't know that the Big Bang is the beginning. That was always a hypothesis. That was never, we don't know that's true from general relativity. We don't know that it's true from our understanding of quantum gravity. It's just a hypothesis that if you take the universe and stretch it back and follow it back in time, it will eventually converge to a, well, if you believed Einstein's theory all the way back to that point, it would converge to a point, and then somehow that would be a beginning. But maybe it's not. We don't know that. We know that, in fact, Einstein's theory is incomplete. It doesn't even include quantum physics. So we know as we reach that point, there's some point where quantum physics comes in, but we don't know yet we don't have yet a quantum theory of gravity in hand, so we can't say for sure what happens at that point. So it's reasonable, if you don't like what happened, if you're not satisfied with it, to contemplate the alternative possibility. The Big Bang is not the beginning, and then see where that leads you. In particular, they would cause the background radiation to become polarized, and this is kind of a cartoon to represent looking with Polaroid lenses at the microwave background of this radiation from the early universe. You would find they would leave a certain polarization pattern of radiation if they were there in the sky. Now, an inflationary model predicts that there should be strong gravitational waves. The cyclic model, this collision between branes, has the property that it produces almost zero-strength gravitational waves. So one of the key things you want to do is check whether these gravitational waves exist, which is to say, check whether or not the characteristic polarization pattern you would expect to exist in the microwave background is there or not. So if you would look at the sky with this radiation from the early universe with polarized glasses, they should produce a kind of swirling pattern of radiation, okay, that we should be detectable. That's what we're looking for. So there are experiments in space, called the Planck experiment in space, which I think I have a picture here, the Planck satellite experiment, which was launched last year and which is beginning to make measurements now, which is looking to see if it can, with polarized detectors, detect whether there's this gravitational wave imprint there or not. If it sees it, then the cyclic ideas are dead because they can't produce that kind of effect. And if they don't see it, then that adds support to the cyclic picture. It kind of points us in that direction. So this is an example of a key test. There's a second test which I won't describe, but there's two different tests we can do, and this is one of them. So we don't have to wait around forever to decide which is correct, because between the Planck satellite and experiments being built on the ground, on mountaintops, and being launched by a balloon in Antarctica, we hope to really learn the answer in just the next few years.
우주 탄생의 비밀을 풀어줄 중력파의 흔적을 발견해 전 세계 과학계를 놀라게 했던 국제 공동 연구진이 10개월 만에 연구 결과를 철회했습니다.
We see these strange patterns that are not expected, in inflationary theory, the simplest inflationary theories. It may be that we've been fooled, that inflation didn't happen.
What's surprising in Planck's latest findings, and is inconsistent with prevailing theories, is the presence of unexpected large-scale anomalies in the sky, including a large cold region, stronger fluctuations in one half of the sky than the other, and less light signal than expected across the entire sky.
When you look only at the large features on this map, you find that our best fitting model, our best theory, has a problem fitting the data.